My name is Nicholaus Trotta, and for my project I did simulations of positron distributions from a polarized electron beam. I worked with Dr. Joe Grames at Jefferson Lab. We used a Monte Carlo toolkit called GENT4, which simulated different physical processes. The initial beam was an electron beam that varied in energy from 10 MeV, 100 MeV, and 1000 MeV, and would hit a target made of tungsten that varied between 0.1 millimeters and 14 millimeters. We then graphed these for their yield and a figure of merit which depended on the polarization. We then cut these graphs using two different cuts, one in momentum, which cut it at 10%, and the other was an angular that was for 10 degrees.
The GENT4 simulation used two different physical processes that were important to our work. The first, Bremsstrahlung, or the deceleration of electrons near atomic nuclei to produce high-energy photons. Second was pair creation, when a high-energy photon would create an electron-positron pair. Once our electron beam hit a target to produce positrons, electrons, and photons, we were able to graph the yield of these per how much electrons we shot at the target to produce a graph versus momentum, which is the first graph you see in the GENT4 simulations. Second, we needed to graph the polarization of these particles as well, and that is the second graph underneath the first one. As you can see, the yield has a higher peak at lower momentum, while the polarization has a higher peak at higher momentum, and it becomes a balancing act of these two features that are important for creating a polarized positron beam. When doing the single target results, we used three different electron beam energies for our initial beam. They were at 10 MeV, 100 MeV, and 1000 MeVs. This required us to look at the yield at each of these different energy levels. And as you can see, the yield peaked at different thicknesses for each of our targets. The first 10 MeV peaked at 4 millimeters, the second 100 MeV peaked at 6 millimeters, and finally the 1000 MeV peaked at 12 millimeters. But again, we need to look at this polarization as well. And this required creating a figure of merit, which was the yield times the polarization squared, so we can get a better look at the peak thickness for each of these yields. And here we can see that the 100 MeV, 1000 MeV, and 10 MeV all peaked at the same values as they did for the normal yield, which is good for when we wanted to create a polarized positron beam. Two different cuts were made. The first was an angular cut of a 10-degree cone that would limit the amount of positrons collected. This is useful for actually creating a positron beam, as only a limited number of positrons can be collected at a time. The second was a cut to the momentum at plus or minus 10%. This will change the shape of the yield and figure of merit, requiring lower target thicknesses.
To conclude, more simulations are planned, and they need to look at the dependence at the 10, 100, and 1000 MeV cases with these cuts. I would like to thank the people at Jefferson Lab, funding from JSA, and Duquesne University. Thank you.